Okay, so next up on our little kind of whistle stop tour of integration is integrating exponential functions. So I suppose we've looked at kind of the initial integration, we've looked at kind of that definite integral as a concept on its own, and then really if exponential and trigonometric are the two, I suppose, that we have to look at, that we would have looked in differentiation as well. And I would say to you, the key thing with integration really, on the whole, but particularly for exponential or trig functions, is to kind of keep in the back of your mind what you would do if you were differentiating, because integration, as we've said, is kind of the opposite of differentiating, so the rules are very similar as well. So the rules are nearly going to be the same as kind of doing the opposite. I suppose we're following that idea nearly in setting out these rules, is what I mean, I suppose, by that. So for exponential functions, for example, when we were differentiating an exponential function, so let's say, for example, y equals e to the power of 5x, if I wanted to find the derivative of that function, I would have kept the exponential function as it was and multiplied by 5, which was the derivative of 5x. And that's, I suppose, a simplified version nearly of our chain rule to some extent here. So we end up with that kind of reduced version of 5e to the power of 5x. Okay, so when we're integrating, we are going to nearly do that rule backwards, or that rule in reverse. So we're accounting for the fact now that if I start with 5e to the power of 5x and I want to integrate it, well, I know an exponential function, or I know, I suppose, first of all, one of my rules for integration is that a constant term can be factored out. I'm just integrating the e to the power of 5x. And I know that an exponential function, when it's integrated or differentiated, remains the same. Now, normally, or when I was differentiating, I would have multiplied by that 5. So to integrate, I will divide by the 5. And we indeed are brought back to the e to the power of 5x that we started with. So I suppose that's the first rule to bear in mind, is that if we have an exponential function which has a term in front of x, a constant coefficient of x there, we will divide by that derivative of that angle part, as opposed to multiplying as we would have done for differentiation. The second little part then is for integrating a function that is not doesn't have base e, so isn't kind of a natural exponential, so any other base. And again, there's just a specific rule for that. So a to the power of x, if we're integrating that, it goes to a to the power of x over ln of a. And then my plus c obviously included for all of these here, because they're not definite integrals. I'm not given any upper or lower bounds for them. So we'll get into some examples here just to see that in practice. 5e to the power of 2x. So looking at this one, we can kind of apply, first of all, what I was saying just there about a constant term. So if there's a constant term in front of an integral or multiplied by an integral, we can actually nearly factor that constant term out and just treat the integral of e to the power of 2x, making sure we multiply our end result by 5. So going at that, that's going to give me 5 times e to the power of 2x just remains the same, but I must remember to divide by 2 as opposed to adding 2, as we would have done if we were differentiating, or as opposed to multiplying as we would have done if we were differentiating here. So filling that out, 5e to the power of 2x over 2 plus c. Okay, and plus c here. I could multiply 5c, but since c is kind of that constant term anyway, it's nearly kind of incorporated within that regardless. Looking at the next part here, so again, we'll start by doing our integral. So 3e to the power of x, that's simply just going to go to 3e to the power of x, so there's absolutely no change. And the 4 becomes 4x when integrated here. This is now to be evaluated at 5 and 2, so that's 3e to the power of 5 plus 20 minus 3e squared plus 8. So that's 3e to the power of 5 minus 3e squared plus 12. Okay, and that's our overall answer here for that, or plus 20, yeah, plus 12, sorry, I'm correct. Okay, so continuing onwards then to the last example here. 8 to the power of x, so I'm noting here that that is not base e, so if I'm looking at my rules, I need to use the third rule that we have here, which means that that function, when integrated, will go to 8 to the power of x over ln of 8, and evaluate then at 0 and 2. So that's 8 squared over ln of 8 minus 8 to the power of 0 over ln of 8. And if we wanted to kind of reduce that down, it goes to 63 over ln of 8. Okay, 8 squared, of course, 64, and then 8 to the power of 0 is 1. Okay, let's go into then 2 exam questions, just again as some short, kind of snappy examples here. Evaluate this integral and give your answer in a specific form. So again, a typical kind of question, maybe do the integral, but also present your answer in a particular format to tie in a little bit of algebra to your question then. So we'll start with the integral. So I'm doing 12 times the integral from 0 to 2 of e to the power of 3x dx. From our rule that we've been looking at in this video, I suppose, e to the power of 3x stays the same, but is divided by 3, and then to be evaluated at 0 and 2 here. Okay, now we can take the 12 in at this point and do 4 e to the power of 3x to be evaluated at 0 and 2, just if we're afraid maybe of forgetting about the 12 there as we continue onwards. We also could have worked out the function and multiplied our two answers by 12 and equally gotten the same answer, but no harm to get rid of the fraction now when we can. So 4e to the power of 3 times 2 minus 4e to the power of 3 times 0. So that's 4e to the power of 6 minus 4e to the power of 0. Okay, so let's continue onwards. 4e to the power of 6 minus 1 or minus, I suppose, 4 times 1. And we can also factor out 4 here to get e to the power of 6 minus 1. So we have our answer and presented in the format as requested in the question. Last little example here. I actually think I'm just missing a part of the question. It's supposed to be equal to e. We're missing just a little bit of the question there. So prove or work out the value of b if all of this is equal to e overall. So we need to start by integrating our function. So it becomes b e to the power of bx, and then where I would normally differentiating multiply by b here, I then for integration divide by b. So that gives me e to the power of bx to be evaluated at 0 and b, which is e to the power of b times b minus e to the power of b times 0. And all of this should be equal to e. So e to the power of b squared minus e to the power of 0 should be equal to e. E to the power of b squared minus 1 should be equal to e. We can go e to the power of b squared should be equal to e plus 1. Okay, and we can kind of take it that bit further. Now I might look at converting this to log format. Okay, and the reason I'm thinking this is because the term that I want is in the power here. Okay, the b squared. I want to work out the value of b, so in order to get that onto kind of a level where I can actually work with it and solve for it, I'm going to have to convert to log format. So I'm going to go to ln, which is base e. Okay, so that's base e. So I'm basically saying that for this function, base e of e plus 1 is equal to b squared. So basically saying here, if I raise e to the power of b squared, I should get e plus 1. And then b, of course, will be the square root then of that. Okay, and taking plus or minus as well to account for the possible values of b. Of course, we know then that b is positive, but just ensuring then that we follow that idea here, and we can give it as a decimal format either if we need to. 1.146. Okay, and we weren't really given any guidance in terms of decimal points there. Okay, but main thing really for exponential functions, and we'll see it again with our trig functions, be aware and have in the back of your mind, what would I do here if I was differentiating? So I would multiply by the exponential or the derivative of the exponential part. So because we're integrating and doing the opposite and working in the opposite direction, we will now divide by that derivative of the exponential part. So still the derivative, still the number in front of the x, but rather than multiply by it now, we will divide by it.